Hello, geometry students. Mrs. Myers here. Today we are going to go through lesson 11, which is a combination of what we did in the last lessons 9/10 with finding areas of polygons, but also what we did right before that with lesson 2, which is graphing inequalities. So since really it's been lots of days since you graphed inequalities last, we're going to do a quick little review here. That's what these opening exercises are about. So let's get at it. First thing we want to remember is that when we only have y or only have x in the inequality, that the boundary line is not diagonal. In fact, when it only has the y, okay, so our boundary line for this would be y is equal to 5. Okay, so that's horizontal. So we go to where y is 5 on the y-axis. So there's the labeling of the x and y-axis. So 1, 2, 3, 4, 5. And we want to make the boundary line. Now, there are two choices for boundary lines. There's either dotted or solid. Okay, so the solid boundary line, okay, that always has the equal to with the inequality. Okay, so it's one of those two choices. Whereas your dotted boundary line, so dotted meaning not to include it, means you don't have the equal to. So you have either one of those two inequalities, okay? So this has the equal to, so you want to include this boundary line, so it is solid. Oops, sorry about that. By all means, if you have a ruler, you can use a ruler to draw this line here. And then we have to do some shading. So in terms of the y's being less than or equal to 5, well, that would mean that the y's would be lower, okay, right? And we would want to shade below that horizontal line, okay? Whereas when there's only the x, now it's vertical, okay? So in this case, our boundary line is the equation x equals -3. So I label my axes, okay, go to where the x is -3, it's right there. But this time, see how there's no equal to? So I'm not going to have a solid boundary line. I'm going to have a dotted boundary line, okay? And then the shading is according to the x's. So I want my x values to be greater than -3. So where the x values are greater than -3 is going to the right. So now that's where my shading goes. All right, and with the next two, notice how the inequality has both x and y in it. So that's going to be diagonal, okay? So what's nice about part C, okay, is if we just write our boundary line equation as y equals -2/3 x plus 5, okay, which I know is going to be solid because I have the equal to here, okay. This is in slope-intercept form, right? This is in y equals mx plus b form already, which is great. So I know that my y-intercept is 5. Okay, don't forget to label your x and your y-axes. Okay, so I can put my starting point right there. And I know that this -2/3 is my slope. Okay, remember slope is rise over run. Okay, change in y over change in x. Now that negative goes with either the numerator or the denominator, not with both, or else a negative over a negative would be a positive. So if I do -2/3, that means down 2, but right 3. So down to right 3. And if I had more room, I could also think of this as +2 over -3, which would mean up 2 and left 3. And again, this is a solid boundary line. Okay, so there we go. Now the shading, okay, the shading has to be for the y's to be greater than or equal to -2/3 x plus 5. Okay, so it's according to the y. So if the y's are going to be greater, then I want to shade where the y's are going to get higher, which means I'm going to shade up. Okay, I'm going to shade above that. Right? Never left or right when it comes to a diagonal line, okay? The only time we ever think about shading going left or right is when it's a vertical line. Otherwise, because that's according to the x's, and the x's go left and right. But when the inequality is according to the y's, say horizontal or diagonal, okay, because you always want y equals mx plus b when it's diagonal, then the shading is either up or down, because the y's are either going to get greater, the y's are going to get less. Now, if you're unsure, remember something I told you before, is you could do the test point. Now, I think the easiest test point, as long as it's clearly on one side of the boundary line or the other, is the point 0, 0. Okay, is you could just put it right in for 0 for the x and 0 for the y. Just see if this is true or not. Okay, so anything down 0, 0, So then this would be 0 is greater than or equal to 5. No, 0 is not greater than or equal to 5. That's false. So this point 0, 0 should not be where my shading is, and therefore I am correct by shading this side, above the line. Okay? All right, so one more quick review here. So this boundary line, okay, is x minus 2y equals 8, but that is in standard form, right? Ax plus by equals c, and that doesn't really help us for graphing much, so I want to get this in the slope-intercept form, y equals mx plus b, so I'm going to isolate the y term first by minusing the x, okay, and I'm going to isolate the y variable by dividing out the -2. Now that means I've got my negative x being divided by my -2, and I've got my positive 8 being divided by my -2. So now this is positive 1/2 x, because there's really a 1 in front of that x. And then this is a -4. Okay, now it's y equals mx plus b. Okay, so I've got my labeling of my axes. I've got my y-intercept of my -4. Okay, so that's why I can have my starting point down there at -4. This is my slope, right? Change in y over change in x. And I'm going to go up 1, right 2, up 1, right 2, because it's positive, positive. Or I could go down 1, left 2, down 1, left 2, right? Because then it could be negative, negative. Now, this boundary line is not solid. I don't have the equal to there, right? So this is a dotted boundary line. Okay. And I'm not thinking shading left or right. I only think shading above or below when it's a diagonal line. So let's look at this, okay? If I had had this greater than kept here the whole time, okay, and I was getting my inequality, well, actually, let me just go here. Like, so if I had this as a greater than, right, and I subtract the x, that's fine. That would still say a greater than, okay? But then in this step right here, where I'm dividing by the -2, that division by that negative would cause that inequality to flip, okay, to switch to a less than, which now would mean that I'd want the shading to go below to be less, okay? So that's your quick little review. So now let's get into 2 different practice problems where we are going to make our own polygonal region that we want to do some calculations of things, okay? So here we go. We got a system of inequalities. We got 4 different inequalities here, and we're going to sketch the region. Now, the first thing that you hopefully notice about these 4 inequalities is that 2 of them are in slope-intercept form and 2 of them are not. Okay, so as we just talked about only a second ago, let's see about getting them into slope y equals mx plus b form. So we're going to take 2y minus x greater than or equal to -6. Okay, I might as well just leave it with the inequality. This way we make sure any flipping of that needs to be done, we would do that. So first is isolate the y term by adding the x. Okay, then isolate the y variable by dividing out the coefficient of it. And when you add or subtract, that never causes the inequality to change. If you're dividing by just a positive, that doesn't change the inequality either. Only if you're dividing or multiplying by a negative, which we're not. So this stays greater than or equal to. So that 2 divides into the x, which the coefficient is a 1, so it'd be a 1/2 x. The 2 also divides into the -6, which is at -3. So there's my y-intercept, there's my slope. Okay, this is already in y-intercept with the slope. This is already where I have my y-intercept with my slope. I got to do one more. Okay, so again, isolate the y term first. Okay, and adding and subtracting never changes that inequality. Then divide out that -3, okay, to get the y all by itself. But notice again what I'm dividing, that is negative, so I do have to switch that inequality to be greater than or equal to now. So -3 divides into the 12x and divides into the 36. So I'm now going to have -4x and -12. So this is now y-intercept, and can put that -4 over 1 to be a slope. All right, so let's graph all 4 of these. So let's just go left to right. So -3 for that y-intercept, that's right there. 1/2 for the slope, so up 1, right 2, up 1, right 2, up 1, right 2, okay, and then this is going to be a solid boundary line. In fact, they all have the equal to, so they're all going to be solid boundary lines. Okay, you could also go down 1, left 2, down 1, left 2 to continue this. And then that shading is going to be above. See, y is greater than or equal to. All right, so shading goes above there. All right, next we have our y-intercept of 5 with a slope of negative 5 over 6. So down 5 and then right 6. And notice I hit that line right there. That's great. I could also go up 5 and left 6. 1, 2, 3, 4, 5, 6. All right, so I'm going to have these points all connected with a solid line. And since this says y is less than or equal to, I'm going to shade below. So that's this shading right there. Okay, next is y is less than or equal to 1/4 x plus 5. So back to, again, that y-intercept of the positive 5. But this time I'm going to do a 1/4 slope. So up 1, right 4. I could do that again. Up 1, right 4. Or I can go down 1, left 4, down 1, left 4. And again, this is a solid boundary line because it's got the equal to, and that shading is less, right? So I'm going to go below that line. And one more right here. Remember that came over to this y-intercept form. I've got negative 12, okay? So unfortunately, I got to extend this by just one line. Sorry about that. So I got negative 12, and then I got negative 4 over 1 for my slope. So that would be down 4, right 1, or it could be up 4 and left 1. So 1, 2, 3, 4, 1, 1, 2, 3, 4, 1. Notice how I hit that boundary line perfectly. That's great. 1, 2, 3, 4, left 1, 1, 2, 3, 4. Actually, 1, 2, 3, 4, 1. There we go. So I hit that boundary line perfectly there. And then I'm just going to get those all connected there. And then this is y is greater than or equal to, so I'm going to shade above. So I know this looks very, very close to being vertical because it's got such a steep slope there, but above kind of looks rightish, so that's shading right there. Okay, so if you see where all these shaded regions intersect, okay, that is right in here. Let me just darken that up very nicely. Okay, so this is the region that we are now going to do a couple different things with. First, we're going to determine the vertices of it, which just basically means these corner points. Okay, what are those coordinates? So this one is negative 4, positive 4. Okay, then we're looking at this one right here, which is negative 2, negative 4. Okay, now we got this one right here, that's 6, 0. And we got this one right up here, that is at 0, 5. All right, then it says determine the perimeter. Now, when we do perimeter, okay, we are going to find the lengths of each of the sides, and we're going to add them up. So this brings us back to our formula for finding the lengths of all the sides, okay, that are diagonal segments. So this is distance equals square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, and we are going to, why don't we call these some coordinates here? Okay, why don't we call this A, B, C, and then D. So let's come here and call this A, B, C, and D, because this way now I can name all the sides that I want to find the lengths of. Okay, so I'm going to do AB first, and that is the square root of, so here are my x's. All right, so I'm going to go negative 4 minus negative 2 quantity squared. And then here are my y's, 4 minus negative 4 quantity squared. And then I do negative 4 minus negative 2, which means really negative 4 plus 2, and that is negative 2 quantity squared. Here I've got 4 minus negative 4, which really means 4 plus 4, so that's 8 squared. Notice how I kept the use of the parentheses. Then this is negative 2 being squared, that's positive 4. 8 squared, that is 64. So this is the square root of 68. Okay, so then I keep going with the length of segment BC. Okay, so that was A to B from here to here. Okay, that's square root of 68. Of course, it's a little over 8. Okay, like it's 8 point something. Sorry, I forgot to actually put this in my calculator to know what this is, but you can easily just put that in the calculator and figure out what that is to the nearest hundredth. So it's like 8 point, whatever. So now let's do BC. Okay, so going from here to here, and that's these coordinates. So I'm going to, for example, go 6 minus -2 with x2 minus x1 quantity squared, and then make sure you keep the same order for 0 minus -4 when you do y2 minus y1 quantity squared. So it really doesn't matter which you pick as your first point and your second point, you just want to remain consistent with your work. So now I've got minusing of the negative, which is positive, so that's 8 squared. Again, minusing the negative is positive, so there's 4 squared. And then this is 64, this is 16. And so this is a square root of 80. I apologize. Sorry about that. So this is square root of 80. Sorry, I just swallowed down the wrong pipe for some reason. Anyway, since that's almost 81, almost the square root of 81, that's almost 9. So you got, again, 8 point something, it's probably 8.9 something. Okay, you can just put that in your calculator. All right, 2 more to go. Now we got CD. Okay, we want to find that segment. And that is going to be 6 minus 0 quantity squared plus 0 minus 5 quantity squared. So that's just 6 squared and -5 squared. So that is 36 and 25 and 61, square root of 61. All right, so last but not least is a D. Kind of squeezing this in here. Sorry about that. All right, so we've got -4 and 0. And I'm going to go 0 minus -4. So with that, I'm going to go 5 minus 4. Sorry about being so smushed down there. All right, so now this would be 0 minus -4, or +4 squared. This is 5 minus 4, which is only 1 squared. All right, so now we're looking at 16 plus 1, and that is the square root of 17. Right, and then of course this is going to be a little over 4, because square root of 16 is 4, and then you just put it all in your calculator and see what you get, and then you just write down your final answer of perimeter. Okay, sorry, I forgot to get my final calculations. I don't have my calculator with me right now, but you can easily do that. Okay, so now we're going to find the area of the shaded region. So as we had said before, okay, we're going to do either composition or decomposition. So composition is when you break this up into rectangles and right triangles and put all those areas together. Decomposition is when you box it in. I personally think that decomposition will work out rather nicely for this. So if I just take this vertex here with D, I go straight across to where I get to A, and then I go straight down until where I meet up with the B, and I go straight across until I meet up with the C, and I go straight up until I meet up to where the D would be. And then I just finish going straight across to the D. There's my box. All right. So first I'm going to do is find the area of the box. Okay, the rectangle, which is done by doing length times width. And if I just count boxes here, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So the whole thing is 9. Remember that was 5 and that was 4. So the whole thing is 9. Okay, then 9 times, so across the bottom here, so this is 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, which makes the whole thing 10. So I know my entire box is 90 square units. Now I've got these 4 right triangles here. Let me number them. This is 1, 2, 3, 4. And what I'm going to do is I'm just going to find each of their areas separately. So we've got area of triangle 1, area of triangle 2, area of triangle 3, area of triangle 4. That's always going to be with that 1/2 base times height formula, right? So bases and heights are always perpendicular to each other and perfectly, except I've got all my right angles here with the horizontal and the vertical segments. So this is 5 units here. So let's count boxes. 1, 2, 3, 4, 5, 6. All right, so half of 5 times 6 is 15. Number 2 is the 4 by 8, right? So 4 times 8 is 32. Half of that is 16. All right, triangle 3 is 2 by, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 2 by 8. And 8 times 2 is 16. Half 16 is 8. And then lastly is triangle 4, which is 1, 2, 3, 4 by 1. All right, so half of 4 by 1 is 2. So I'm going to add all this together, 15, 16, 8, and 2. So that makes for 41 square units. So now I just have to do the 90 minus the 41, and I get my answer is 49 square units. Okay, so that is the area of that region. All right, I got one problem left to go for our notes. Okay, so now I've got this shaded region, but the first thing we're going to do before we find the area of it, see, this is find the area, is we're going to identify this system of inequalities that defines this region. So 2 of these inequalities are going to be very, very easy to write. Okay, here's our x-axis, here's our y-axis, because this boundary right here is horizontal, which means it's a y equals boundary, and it goes through this y value of -1, so that's going to be easy to write the inequality. Okay, this boundary line right here is vertical, so that's an x equals equation, and that is again through an x value of -1. Okay, so those are both very, very easy. I'm going to write the system of inequalities here. This is solid, and I'm shading above this horizontal line, so this is y is greater than or equal to -1. Okay, this is vertical, okay, so it's again the x equals equation, x equals -1, and I've shaded to the right of it, so this x is greater than or equal to -1, pardon me. Now this diagonal line right here, though, it really shouldn't be too terrible to write the equation of it if I had a nice y-intercept, okay, nice integral y-intercept, but I don't, okay. If you look this here, I do not see this crossing the y-axis at a nice pretty little point. It's in between 2 integers, and I'm not just going to approximate that. So what I want to do is I want to find 2 points that are on this line, and then I can easily write the equation that goes in between those 2 points. We learned how to do that lots of lessons ago, so I'll do a nice review with this. So I'm actually just looking at the vertices here that define the shaded region, and I'm thinking those are very easy coordinates to write. This one is to the right, 1, 2, 3, 4, 5, 6, 7, 8, and down 1. So this is 8, -1. And this is to the left, 1, and up 1, 2, 3, 4, 5. So this is -1, 5. Okay, so now that I know those 2 points, can I write the equation of the line that goes through them? So first thing I'm going to do is I'm going to find the slope. My slope formula being y2 minus y1 over x2 minus x1. Okay, so I'm going to find the slope as, and I'm going to do the y's first, so 5 minus -1. That's how I'm choosing to do y2 minus y1, which means I'm now going to do the x's in the same order and go -1 minus 8. So this is 6 because it's minusing of the negative. Here, if I want, I can add the opposite and think -1 minus 8 is -1 plus -8, which is -9. And then I'm going to move that negative into the numerator. It's just a little more common than leaving it in the denominator, and that can reduce down to 2/3. Okay, so now I got my slope. This is my m. But again, I'm not ready to write slope-intercept form yet because I don't have this nice y-intercept. So I'm going to use point slope form. I'm going to go y minus y1 equals m times x minus x1. And I know 2 different points so far that are on that line. There's probably other ones in there, but these were very, very nice and easy to identify. I can pick any point, either one of these, and call that x1 and y1 on the line. So I'm just going to pick this. I'm going to pick -1, 5, and then you need the slope, right? That's your m, okay? So I go y minus 5, see, because that's the y1 coordinate, and then -2/3 is my slope, and then x minus -1, right? Because again, I'm using this point, so this is my x1 comma y1, right, point that I'm using for point slope. Adding the opposite with minusing the negative turns that into a positive 1. So now I'm going to distribute that negative 2/3. So it's negative 2/3 x. And then since this is positive 1 that you're multiplying by negative 2/3, that's still negative 2/3. And I'm going to add the 5 to get this into y equals 4. And y equals mx. Here's my mx. See, here's my slope, right? Mx plus b. So what's my b? What do I get when I add this together? So let's change 5 into 15/3, okay, because that's a common denominator. Now I can put those two fractions together as 13/3. So there's my b, right? There's my y-intercept that I didn't want to approximate before, but now I know exactly what it is. So I'm going to go to write my inequality, and you see how the shading goes below that line? So it's y is less than or equal to negative 2/3 x plus 13/3. Okay, so the inequality is going to be less than because the shading goes below that line. Okay, all equal to's because they're all solid lines. Okay, so that's the system of inequalities. Now I want to find the area of the region. Well, what's so nice is this is a right triangle, so I can just use the area formula of 1/2 base times height. Okay, I don't have to use composition or decomposition here because this is a right triangle. So this base right here, okay, is 9 units long. See, if I was to count the boxes going from -1 on the x-axis all the way to 8 on the x-axis, that would be 9 units long, okay? And then this height right here, this goes from -1 on the y-axis to +5 on the y-axis. So that's 6. If I count the boxes, that's 6 units of height. 9 times 6 being 54, and half of 54 being 27. And that is your area. Okay, so hope everything went well for you with this lesson. We went through and did a lot of different things here. Okay, so this is the last one on finding area, but definitely not the last one in this module using all these formulas and things with equations of lines. Okay, so you've got a problem set that follows with what we just did. Okay, it's only 2 questions. But take your time and make sure that you are nice and neat and accurate with everything. All right, and then post your work by the end of the day. All right, hope all is well. Bye-bye.